Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss Fresnel's half period zones for plane waves. Let's begin. In previous video, we discussed about Fresnel's assumptions. According to Fresnel's assumptions, if we consider a source S, the light waves are emitted from that of source having the wavelength lambda be the wavelength of light at a large distance. According to Huygens principle, that particular light wave is treated as a plane wavefront. A, B, C, D is a plane wavefront. That is the direction of propagation of light. According to Fresnel, that wavefront is divided into large number of strips, which is known as Fresnel's strips or zones. Taking a point O, there are large number of strips let me consider a point P which is at a distance x from that of point O. Point O, that is known as the center, the pole of that of wavefront. The pole of that wavefront with respect to P, point P, and these poles and these concentric circles have at a distance, this is the first concentric circle, have at a distance first one x plus lambda by 2, next one x plus 2 lambda by 2, successive path difference lambda by 2, next x plus 3 lambda by 2, next x plus 4 lambda by 2. If we take such n number of Fresnel strips, it has x plus n lambda by 2. And the points are basically named as, here let M1, that point let M2, that point M3, that point M4 for nth point, that is Mn. These strips or zones are further named as half period zones. Why we named like this half period zones? Look at that particular figure. And the area in between two spheres is called the half period zone. That be the area between a sphere again. These are the area between the sphere, area between the sphere, here is the area between the sphere. These are named as half period zone. Why we named such? The area between two spheres is called half period zone. The name half period. Look here, any two concentric spheres or circles have a path difference of lambda by 2 and the time period also differ as t by 2 and the phase differ as pi. Here wavelength differ as lambda by 2, time period differ as t by 2 and phase differ as pi. This is the wavelength, that be the time period, again that be the phase. For a complete cycle, complete wave, we have the phase difference 2 pi, its half, that is pi. Therefore, the name of these Fresnel strips or zones are further named as half period zones. Since the waves from the corresponding points of the adjacent areas differ in path by half wavelength the annular rings in the wavefront are called half period zones. Half period zones, or simply, as you know, in case of Fresnel's assumption, simply these are the Fresnel's zones. Fresnel zones. In that Fresnel zones, Fresnel zones or half period zones, the waves reach the point with a time delay of half time period. The adjacent areas differ in path by half wavelength. The annular rings of that of wavefront is also called half period zones, simply Fresnel's zones. In that of Fresnel's zones, the wave reaches the points with the time delay of half time period. Therefore, the name of the Fresnel strips are known as half period zone. We have to calculate what be the resultant intensity due to that plane wavefront at point P. To calculating the resultant intensity, first we calculate what be the radii of a half period zone. Radii of half period zone. Radii of half period zone. Let the radius of nth half period zone is OMN. From that of triangle OMNP, which is a right angle triangle, we can use the Pythagoras theorem to evaluate that radius OMN. For nth half period zone, radius OMN is equal to PMN square minus OP square square root, as from triangle OMNP we use the Pythagoras theorem. PMN square, that is x plus n lambda by 2 square, x plus n lambda by 2 whole square minus OP square, that is x square under root. Now a plus b whole square, here x square plus n square lambda square divided by 4 plus 2x n lambda by 2 minus x square under root. Here x square cancel out. Inside that a bracket we have here 2 to cancel out. So n square lambda square by 4 plus n x lambda under root. Since n is a natural number, its square also a natural number, and that particular term is neglected. N square lambda square 4 is very small. So it is neglected. Therefore, we have n x lambda under root, where n is a natural number. This is the radius for nth half period zone. Similarly, for first half period zone, that is 1 x lambda under root. For second half period zone, the radius will be 2 x lambda under root. For third half period zone, the value will be 3 x lambda under root, so on. From that of expression, we conclude that hence the radii of half period zones, is proportional to the square roots of natural numbers. The radii of half period zones is proportional to the square root of natural numbers. Next, what will be the area of half period zone? The area of half period zones. Area of half period zones. Let me take the area of nth zone. The area of nth zone is equal to area of first n zone minus area of first n minus 1 zones. If we take the area of nth zone, so the area in between the circle having the radius OMN and also having the radius OMN minus 1, its conjugate. So, area in between these two is the area of nth half period zone. So, the putting these values of areas, we have for the nth zone, that is pi O mn square its radius minus pi O m n minus 1 square. O m n minus 1 is the radius of n minus 1 half period zone, pi O m n square. Here putting the expression n x lambda square, n x lambda minus pi, here n minus 1 x lambda as its square of under root, we have only that value taking pi as common, pi lambda as common, nx minus n minus 1x, pi lambda nx minus nx plus x, nx cancel out, we have pi x lambda, that is the area of nth zone. Look at that particular expression. Here there will be no such term of n, means the area of half period zones are independent of what be the number, means all half period zones have equal areas. We conclude here, hence we conclude that the area of nth zone is independent of the number of zones. And so the area of each and every zone is constant. So the area of each and every zone is constant. The area of nth zone is independent of the number of zones, therefore the area of each zone is constant. Next, what be the distance of a point P from that of half period zone? Distance of point P from half period zone. Look at that particular figure. This is a plane wave front which is A, B, C, D, that be O. Let we take here is the nth half period zone, here is the point P which is at a distance of x from that of pole with respect to that point P. Here that segment is the radius mn and here is the radius m n minus 1, joining these two. So the distance of point P from that of half period zone for nth half period zone is the average distance having P mn and P m n minus 1. So we have, it is given by the distance P mn and P m minus 1, it is given by distance of point P from that of half period zone, that is P mn plus P m n minus 1 divided by 2, that will be the average. That average is named as the distance of point P from that of half period zone. The distance of PMN, which is x plus n lambda by 2 plus for n minus 1 x plus n minus 1 lambda by 2 whole divided by 2. Simplifying that one, x plus x, that is 2x, plus taking lambda by 2 as common, lambda by 2 as common, we have n plus n minus 1 divided by 2. So 2x plus here 2n minus 1 lambda by 2, 2n minus 1 lambda by 2 divided by 2. So 2 to cancel out, here x plus 2n minus 1 lambda by 4, that is the distance of point P from a half period zone. This is distance of point P from nth half period zone. Similarly, putting the values of n, we can calculate each half period zone is situated at what distance from that of observation point P. Next, we have to calculate the amplitude of that of wave front at point P. To calculating amplitude of wavelet at point P. According to FRESNEL'S assumptions, we say that the amplitude at point P is depend upon various factors. What are the factors responsible for the amplitude due to that particular plane wavefront at point P? The amplitude at point P depend upon, which is directly proportional to the area of zone, and also directly proportional, which is inversely proportional to the distance of zone from that point, inversely proportional the distance of the point that of zone. Here area of the zone, which is pi x lambda inversely proportional to the distance of the zone from that of point, which is 1 divided by x plus 2n minus 1 lambda by 4, again directly proportional to the obliquity factor, which is 1 plus cos theta, obliquity factor. Now combining these three, therefore the resultant amplitude at point P, the resultant amplitude at point P due to the zone, the amplitude Rn is equal to, here area of that of zone, which is pi x lambda into 1 plus for nth term, that is theta n cos theta n divided by x plus 2n minus 1 lambda by 4. For large values of n, 2n minus 1 lambda by 4 is neglected. Therefore, we have pi x lambda 1 plus cos theta n divided by x, x cancel out. The resultant amplitude is equal to x lambda 1 plus cos theta n. So, the resultant amplitude increases with the increase in the value for n, and the factor cos theta n will decrease as n increases. So, the amplitude overall R n decreases with increase in the number of zones. This is the resultant amplitude. This is the fact we observe from experiments. From experiments we conclude these facts regarding resultant amplitude at point P due to these half period zones. Let we calculate what be the resultant amplitude at point P due to the entire wavefront. This is the resultant amplitude at point P due to the nth zone amplitude, resultant amplitude, that is R n. Next, resultant amplitude at point P due to the entire wavefront. Resultant amplitude at point P due to entire wavefront. See that of figure. There are large number of such half period zones. We have to calculate what be the resultant amplitude at point P due to that of entire plane wavefront. For this calculation, as we know, since the path difference between two consecutive zones, in lambda by 2, and these two waves, reaches in opposite phases. In opposite phases. Here if I draw that wave, since it has a path difference lambda by 2, if one half is positive, another half taken as the negative, and like that. That is the light here, that is the light from two adjacent half period zones differ in phase by pi. Two adjacent zones differ in path difference lambda by 2 and also phase as pi. So, one is positive half and another one is negative half. Therefore, the resultant amplitude at point P is given by, let resultant amplitude be R. So, R is given by R1 minus R2 plus R3 minus R4 plus dot 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 up to minus 1 to the power n minus 1 Rn. One amplitude taken as positive, another amplitude taken as negative. Here R1, R2, R3 are the amplitudes of various zones. R1 with the amplitude of first half period zone, R2 is the amplitude of second half period zone, like this, these are named. Look here, as we taken the amplitude gradually decreases, the graph just looking like this. Here positive, negative, positive, negative, positive, like that. So, the negative one can be written as the average of two positives. Here we say R2, let R1, R2, R3 like this. So, R2 is which one is negative. So, that is the average of two positives, that is R1 plus R3, R1 plus R3 divided by 2. Next R4 is equal to R3 plus R5 divided by 2 and so on. Therefore, R can be evaluated as, in place of R1 we write R1, in place of R2 we substitute minus R1 by 2 minus R3 by 2 plus R3. Next, in place of R4, that is minus R3 by 2 minus R5 by 2 plus dot 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 up to the term that depend upon what be the value of n, either n is odd or even. Look at that particular expression here. Here R1 minus R1 by 2, which is R1 by 2. Next R3 divided by 2, R3 divided by 2, which is minus R3. So, minus R3 plus R3 cancel out. Like that, another terms R5, R6 all are cancelled out. Only the term exists that depend upon the value of n. Now when n is odd, so R is equal to R1 by 2 plus Rn divided by 2, that will be the last term. When n is even, the resultant amplitude R is equal to R1 by 2 plus the last two term, that is Rn minus 1 by 2 minus Rn by 2. Look at these two expression, here Rn by 2, Rn minus 1 by 2 and Rn divided by 2. For large values of n, we have to neglect these terms. Therefore, for large values of n, both Rn minus 1 by 2 and Rn by 2 can be neglected. Hence, R is equal to R1 by 2. As we say, which is equal to R is equal to half into R1, that is the amplitude of first half period zone, amplitude of first half period zone. So, the resultant amplitude at point P is nothing, that is the half of the amplitude of first half period zone. So, the resultant amplitude at point P, the resultant amplitude at point P is due to the first half period zone and its value is half of the amplitude of first half period zone, first half period zone. The resultant amplitude at point P due to the first half period zone and its value is half of the amplitude of that first half period zone. Next, what will be the intensity at point P due to that of entire wavefront? Intensity at point P due to entire wavefront. We know the relation between intensity and amplitude, as intensity directly proportional the square of amplitude, the square of amplitude, that is I is equal to R square, which is equal to R1 divided by 2 whole square, which is equal to here I1 divided by 4, as I1 the intensity of first half period zone, at point P. That is I is equal to I1 divided by 4. From that expression we conclude that intensity at point P due to the entire wavefront is equal to 1/4 of that intensity due to first half period zone. Thus, the intensity at point P due to entire wavefront is equal to 1/4 of the intensity due to first half period zone. First half period zone. The intensity at point P due to the entire wavefront, which is equal to 1/4 of the intensity due to the first half period zone. As we say here, from that of Fresnel's half period zones for plane waves, the intensity at point P due to that plane wavefront is nothing, that is the 1/4 of the intensity due to the first half period zone. This is the first half period zone. So, with the help of this video lecture, you understand Fresnel's half period zones for plane waves. Why the name like this half period zone? We analyze. It has path difference lambda by 2, time period t by 2 and phase difference pi. Radius of half period zone. The radius of half period zones is proportional to the square root of natural numbers. Next, area of half period zones, which is independent of the number of zones. Each half period zones have equal in area. Next, distance of point P from that of half period zone. As we take the average distance here for nth half period zones, like that of all distances are measured at point P. Next, amplitude at point P. Experimentally, we say the amplitude depend upon various factors, and the amplitude of nth half period zone is calculated. Next, the resultant amplitude at point P due to that of entire wavefront, as we say, the consecutive half period zones are opposite to each other. Taking this concept and clarify the resultant amplitude at point P, which is equal to half of the amplitude of the first half period zone. Next, intensity at point P due to the entire wavefront, which is equal to 1/4 of the intensity of first half period zones. So, with the help of that particular video regarding Fresnel's half period zones for plane wave, we conclude these basic ideas as we first discussed in case of Fresnel's assumptions. So, with this useful and informative notes, let me wind up this session. Thank you.